of DC motors. So previously we discussed the transient analysis, and we derived the mathematical model and block diagram and transfer function also for the DC motor in the mode of separately excited DC motor, which is mostly used in industry. Okay, so or shunt, yani it's equivalent to shunt as well. So today, inshallah, we will start discussing the behavior and performance of separately excited induction DC motor and series DC motor, steady state analysis, speed regulation, and we will discuss the speed control mainly of separately excited and shunt, and the solid state drives used for DC motors. These are the objectives of these slides يا شباب. يعني we may not cover it today, we may cover it in 2 or 3 classes. So يعني let's start in these objectives inshallah. يعني starting first يا شباب for the power flow. يعني you know previously we have many circuits for DC motors. Okay, we have separately excited DC motor, we have series DC motor, we have shunt DC motor. So we have many circuits. The aim, يعني each circuit has its own configuration and own properties. So in order to consider the power flow of the machine, there is a basics we have to take it in consideration. Firstly, all of time the electrical input power will be Vt multiplied by It, whatever the circuit. The input power is considered as the terminal voltage multiplied by terminal current. We will have some electrical losses, شباب. Electrical losses like what? If we have series resistance in the circuit, so there will be IT square multiplied by R series, because the series resistance most of the time will be used in series with the supply. So the terminal current will be will flow in that series resistance. Also, we have IF square RF, and sometimes we have RF plus RFWC or field winding control or rheostat. Okay, so in this case, the copper loss on the field winding will be I square multiplied by the total resistance of the field circuit. We may also have the armature resistance. This is for all types of motors, and the armature resistance all of time will have the armature current. So the copper loss on the armature winding will be I armature square multiplied by RA. So in order to get the copper loss for any resistance you should consider its current. So for series, you have to see the current which is moving in the series winding. For the field winding, you have to consider the current of the field winding. Okay, and for the armature winding, the same. You have to consider the armature current of the armature winding. So this is to get the winding or copper loss. We have also rotational loss. Rotational loss is constant almost. We can make it or obtain it experimentally, and we can assume that it's constant. Okay. We develop the power which is moving from the armature side to the field side, or from rotor to stator, is called develop the power, develop power, EAIA. Okay, this is after considering or calculating the all of the losses, all of the electrical losses. So the power developed that will be converted from electrical to mechanical is EA multiplied by A, where EA is considered as the back EMF or the generated voltage of the DC machine. طبعا يا شباب يعني I think we don't need to discuss DC motors from scratch, because you already familiar with DC motors and discuss it in more details in previous courses. تمام؟ يعني how the motor start and how the motor work, which means the principle of the operation of DC motor. يعني I think you are familiar with that. So we just will cover or will refresh your knowledge about the important relations, the important schemes and power flow for different motors, in order to start immediately in the important part in our course, which is the control and braking of machines. So After getting the mechanical or electromechanical power and considering the rotational loss, the amount of remainder power will be the output power, which is a mechanical output, or we can call it as a shaft power. This is the output power. All of time شباب power output equals torque shaft multiplied by omega, where omega here is the speed of the rotor. طبعا يا شباب here we have DC motor, so يعني nothing called synchronous speed or like that. So we have only one speed in the motor now, which will be the shaft speed. Okay. Also يعني you should be familiar يا شباب with something called armature reaction. Armature reaction is nothing but if you have two circuits, and these circuits are close to each other, and you have current in both of circuits, so there will be an effect. So you have armature current. This armature current will have its own flux, and this flux will affect the other winding, which is in DC motor will be the stator winding, because in DC motor, we have stator windings for field in the stator side, and we have armature winding for power in the armature or in the rotor side. So here you will have armature reaction, which will affect the field winding. The solution for that, we have two different things, which are the compensating winding and damper winding, which are used, sorry, not damper winding, compensating winding and interpole, okay, which are used to compensate the effect of armature reaction. So we can consider that armature reaction will for DC motor is effective because it will reduce the amount of flux, and in order to compensate that, we need to make the compensating windings and interpoles. And the effect of the armature reaction is that it's shifted the EMF from the position, the zero EMF from the position of the brushes. So it's affecting the brush's lifetime and shifted the virtual axis of the machine. So it's very effective in DC motors. We did not discuss it in details in other machines because it's not effective like in DC motors. However, armature reaction is there in induction motor. طبعا induction motor, the theory of the work basically is based on the theory of the induction. So it's nothing but armature reaction. However, in other machines like synchronous machine and DC machine, it has significant effect, okay, on the field. So we have to consider particularly for the DC motors. Fine. So this is regarding the power flow, شباب, and the different configuration of the power flow according to the motor type. In general relations, we can say that B input is VTIT, B developed is P input minus all copper losses. So it will be the summation of any I square R in the circuit. Take care that in the DC motor, we don't have resistance representing the output power. And in DC motor, we had R2 prime over S multiplied by 1 minus S, which was representing the output mechanical power. So this is gained power. However, in DC motor, we don't have a resistance in the equivalent circuit representing the output power. However, the output power or the gained power can be obtained from the EMF multiplied by IA. So we can say that this is the equivalent circuit, for instance, for the separately excited DC motor, like that, for instance. We can assume that we have brushes like that here. So this is V terminal. Here we have armature current. We have RA, we have LA, we have here EA. So we can consider that the element which represents the gained power is nothing but EA multiplied by IA, which is the developed power here, okay? However, there is no resistance that representing the gained power in DC motor. Right. The torque, as we discussed, torque by omega equals the output power, and the torque itself can be calculated as a function of the machine. We will see how we can calculate the torque in the different types, in separately excited, shunt, or series. And the developed power, we said it's equals to EAIA equal torque developed by omega. Okay, this is the developed torque. Okay, However, the output power equals the shaft torque multiplied by omega. So we can say that B friction as well. B friction equals torque friction multiplied by omega, similar to other types of motors, because this is just mechanical representation to the output and mechanical loss. Regarding the equivalent circuit for separately excited or shunt, on the left-hand side, this is a separately excited, what we have discussed last session. We discussed the mathematical modeling of separately excited DC motor, and we drive the transfer function of this type of motor. So we have V terminal equals IARA plus EA. We neglected here LDI by dt, because now we are discussing the steady state response, not the transient response. And you know, at steady state, LDI by dt equals 0. For that, in solving the problems, we can consider Vt equals IARA plus EA at steady state. You have the value of EMF here, which is equal to Ka multiplied by flux multiplied by speed, which equals here, from using Kirchhoff current law, Kirchhoff voltage law, we can say that E equals Vt minus IARA. And also, if we have brushes, so we can consider the brush voltage also as a small voltage drop here. However, because voltage drop on brushes is very small value, شباب, around 1 to 2 volt. And for the high rating machines which we are using in industry, the terminal voltage start from 200 volt to maybe around 2 kilovolts, okay, DC. So we don't consider the brush voltage in these circuits. However, if you are going to work with very small rating motors, because recently we use DC motors in some low power applications and low voltage applications, like for instance, we discussed previously, we used it in solar energy applications, like in concentrated solar power. In concentrated solar power, we have something called the parabolic trough, we have something called parabolic dish, we have something called solar power tower, which is based on mirrors called heliostat that are controlled or moved by drive system. So all of the CSP شباب are based on moving some mirrors. And in order to move such mirrors, the dominant motor used in industry in these applications are the DC motor. And these DC motors voltage is very small, maybe around 24 volt. So if you have such a small volt, you have to consider the brush volt, because 2 volt is a percent of the 24, is a good percent, can be considered. However, 2 volt out of 500, for instance, it's very small and can be neglected. So it's according to the rated voltage. We can consider or neglect the brush voltages. So this is a mathematical model of the separately excited DC motor. If we consider that we have shunt motor, so in shunt motor, the field winding will be connected in shunt or parallel with the armature winding. So as you can see here, we have the field control resistance and we have the field winding itself. So we have a field current, which is a function of the terminal voltage of the motor. If the terminal voltage is constant, all of time the value of field current will be constant. And RFC is used, شباب, to control the value of field current if we change the terminal voltage. So it's basically used to adjust the value of IF. So the mathematical model here in this case, we can say also V terminal equals IARA plus EA, if we apply Kirchhoff voltage law here. However, IA here can be obtained as the difference between the input current and the field current, applying Kirchhoff current law at that node. So IA equals IT minus IF. So don't forget, if you have a shunt motor, to subtract the value of field current if you have the input current. The EMF is also similar. It's Ka multiplied by phi multiplied by omega m, which is the motor speed. We can say also phi equals constant multiplied by IF. So we can say, but this should be K, not Ka. Another constant, K multiplied by IF, by omega r. Okay يا شباب. So this is now the relation of EMF, okay, and Kirchhoff voltage law for the DC shunt motor. يعني it's almost the same, only the current Kirchhoff current law we can use it here to get the armature current as a function of the input current. Regarding the characteristic of the motor يا شباب, in order to get the characteristic, simply in the mathematical model you have يعني EA equals KA phi multiplied by omega equals VT minus IARA. So you can say now omega equals VT minus IARA over KA phi. So just divide by KA phi, okay? And you can say also torque equals KA phi multiplied by IA in order to get the relation between omega and torque. Now, simply, you can apply different value of torque and observe the corresponding value of omega in order to draw the characteristic of the DC motor. In case of separately excited or shunt, you will get this characteristic. This is the steady state characteristic of separately excited or shunt DC motors. Now, you know the relation between omega and torque. From this relation, we would like to recognize what are the possible parameters that we can control in order to control the motor speed. Hey, Shabab, what do you think? What are the parameters we can use now?
Voltage.
Voltage is one, exactly. Okay.
Resistance.
Resistance of the
armature.
How we can control the armature resistance? Armature resistance means the effective resistance of the armature winding. How we can control it? Can we reduce this value? Can we reduce the armature resistance?
I think no.
It's not possible, صح? Or
Yes,
it's difficult to be achieved. However, we can add external resistance to the circuit. In this case, we will control or increase the effect of the armature resistance in the circuit. مظبوط كده يا شباب? So the second parameter we can control is the value of RA by adding external resistance. What else يا شباب?
The field
current.
The field current, exactly. So if we control the field current, we can control the flux. And by doing that, we can control the speed, torque or torque speed characteristic curve. طبعا يا شباب, this is the the right orientation of the torque speed characteristic. Compared to the previously discussed induction motor, we have two shapes. We can make torque in the vertical x and speed in the horizontal x, and this is the most well-known curve in induction motor in most of books. However, in terms of electrical drives, we prefer to make omega or speed in the vertical x and torque in the horizontal x. Why? Because we refer to this standard curve to have quadrants. So this is first quadrant. Here will be the second quadrant, third quadrant, and fourth quadrant. So in order to make names for the quadrant, you have to consider the standard orientation of the curve. Okay? So this is the standard orientation for the drives curve. Speed is in the vertical x and torque is on the horizontal x. So now let's see together, Shabab, how we can make speed control by the different techniques. However, firstly, let's see Faddal.
Sorry, but here is not the speed in the vertical and the horizontal axis and the torque in the vertical axis. So why we switch between them?
If you remember in induction motor, yes, the most well-known curve of induction motors are plotted in this shape. Is it right?
Yes.
Where this is torque and this is speed. So the vertical x was torque and the horizontal x was speed. This is not the standard orientation of the curve for electrical drive. Standard orientation is speed in the in the vertical axis. This is speed, and torque is in the horizontal axis. So this is the standard orientation for electrical drive curves. Okay. For that, if you review the characteristic of induction motor at speed reversal, we plotted the characteristic like that. If you remember, we have omega here and torque here, and we plotted the characteristic like that.
Yes, that's what I mean, Doctor. Why we switch between them, or it's there is no problem if we switch.
There is no problem. It's just rotation of the diagram. However, I just refer to one important thing. If you say quadrant 1, quadrant 2, quadrant 3, so you have to respect the standard orientation, which is omega is in the vertical and torque is in the horizontal. You cannot say that here. Here, if you say that this is number 1, you cannot say this is number 2. This is now wrong, because this is here is considered as number 4. Okay? Because sorry, not here. Sorry, here. This is number 1. You cannot say now this is quadrant number 2, because this quadrant is quadrant number 4, because this is not the standard orientation. You got it?
Yes. That's what's been, we can use the twice representation.
You can use, but don't make don't object the quadrant names if the curve is not standard. Okay. Yes, this is my note here. Right. Regarding series motor يا شباب, just also to refresh your knowledge. For series motor, we have series winding or series field winding connected to the armature winding. So we have R series with N windings series, okay? And we have also sometimes controlling resistance rheostat, series resistance, and we have the armature winding. So all are connected here in series. So this characteristic here will be different a bit, because the field current and armature current now are the same. And now it's load dependent. It's not like in the separately excited or in shunt motors, because in separately excited or shunt motors, we can consider that IF or flux is constant all of time. However, in series, it's not the case, because current here is a function of load. So the field current and flux will be a function of load as well. For that, شباب, we can say here KFI equals K series multiplied by IA, where IA and IF here are the same. So you can say now the EMF equals K series multiplied by IA multiplied by omega M. And you can say now torque equals K series multiplied by IA squared. So the equation, the electrical equation for this motor is EA equals Vt minus Ia multiplied by the summation of all of the series resistances. And you can represent omega M as Vt over K series Ia minus Ra plus R series plus R rheostat over K series. Now, and you can as well make the relation between torque and speed just by replacing Ia by square root of 2. We can say Ia equals square root of 2 T over K series. Represent here or replace I by this relation, T equal K series under square root of 2. So you can now get the relation between torque and speed. Change the value of torque and observe the corresponding value of speed. You can draw the curve. You will find that the advantage of this motor is that at very low torque values, the speed will be very high. And at very low speed values, the torque will be very high. This is very important for the heavy load, شباب, because heavy load needs high starting torque. And the torque or starting torque, which means torque at zero speed, will be very high in case of series motors. For that يا شباب we prefer to use series motors for very high starting torque loads. Okay. Now there is a definition called speed regulation. Just a review. If the load is applied to a DC motor or machine, the speed of the motor decreases automatically. Thus, to maintain the constant speed, the difference between no load and full load speed, called speed regulation, should be maintained very less. So if you can keep or you can design your motor to have small speed regulation, this will be very helpful. Right. What is the relation of speed regulation? Speed regulation is simply like voltage regulation. If you remember, it's no load speed minus full load over full load speed. No load speed, which is considered as the highest value of speed here. طبعا this is شباب for separately excited or shunt. Okay, so the no load speed here can be considered at very small value of a or at zero current. So we can say now it's equal to E over K phi or V over K phi, because we can consider I at no load is very small or equal 0. So this is now the relation of no load speed. However, full load speed, you can obtain it based on the operation of your motor. This is to obtain the value of the speed regulation for any motor. And if the speed regulation is small, this means this motor characteristics or parameters are well designed. it seems the شباب this slide is repeated, so this one can be removed. Slide number 8. I will update it after class inshallah. Right. Let's start discussing the different types of speed controls. Firstly, the adding resistance to armature winding. Adding resistance to armature winding. If you remember, in case of induction motor, we added resistance to rotor winding. Okay. However, here we will add resistance to stator winding because it's effective in the relation of torque speed characteristic. So if we have R external and you substitute in the equation of omega in case of separately excited or shunt motor, we will find that adding resistance here, firstly, it will not affect the value of no load speed, because we said that no load speed equals V over K pi. So there is no function of resistance here. So whatever the added value of resistance, the no load speed will be the same. If you added resistance and check the value of speed at high torque, or at operation, not at zero torque, we can find that the characteristics is moving a شباب like that. So the more resistance you add, the lower speed you get. Okay? So if you add more resistance, as you can see, the speed will be decreased. مظبوط يا شباب? So this is how we can control the speed by adding resistance. This method is simple and attractive for short-term applications. Short-term applications, which means it's not using this motor for long time. Because if you are going to use it for long time, this means the resistance will be added to the circuit for long time. And this is going to affect the system efficiency. And we don't prefer to reduce the efficiency during the operation. Also, the main disadvantage of this method is that the armature losses are substantially increased. This is what we just have discussed. So you can add resistance and make wide range of speed control. However, the drawback is that it's lower efficiency because of the copper loss. This is for the adding resistance. Is it used anymore now in advanced drives, no, it's not used. So this is for conventional shipping. We add resistance in conventional drives, not for advanced drives. Conventional drives, it means we control by adding physical resistance. However, advanced drives means we use power electronic converters to control the motor speed. Okay, شباب? So in the new or recent drive systems, we do not add resistance in order to control the motor speed. But you can find it in all the factories. If you could find DC motors in all the factories.
Doctor?
تفضل.
The method that we use in the induction, the slip recovery, can be used here?
Slip recovery. Slip recovery was made in induction motor because you already have another windings and you can return the energy to supply. However, here you have one circuit. And you don't have two circuits to think about that. And in induction motor, you have two circuits and you have circuit and rotor, and in order, and instead of dissipating the energy in the added resistance, we thought to return this energy to supply. However, here you have only one circuit and this circuit is already connected to supply. So it's meaningless to start thinking, can we replace the adding resistance by returning the energy to supply again, because it's already connected to supply. تمام?
Yes.
But it's a good thinking to think about that here in class. احييك ان انت فكرت في حاجه زي دي. ممتاز. Next technique يا شباب is the terminal voltage speed control. And this is the most one used in industry this is the field one. These are the most two techniques used in industry in the electrical drive systems with power electronics. طيب, let's see together how we can change the voltage and what is the effect of the voltage. How we can change the voltage may be discussed in the next classes, okay? But today we will discuss the effect of changing voltage. So, as you can see here, if we have certain voltage here, VT1, and we reduce the voltage, you will find that that no load speed equals V over Ka-phi. So if you reduce V, the no load speed will be decreased. So this is no load speed at rated volt for instant. This is smaller one, smaller, smaller, and so on. So the direction of increasing volt is this الراوي شباب. So this is the direction of increasing terminal voltage. طبعا يا شباب, as we discussed previously, it's not preferred to increase the voltage over 5 to 10% over the rated. Otherwise, you may affect the insulation materials of the windings. So we can only reduce, not increase the voltage. Increasing voltage is very, very limited. For a constant load, first, if this method of speed control, the field current IF, in this method, the field current IF is kept constant. And the armature terminal voltage is varied to change the speed. We discussed that in case of shunt motors, شباب, if you reduce the terminal voltage, the field current will be reduced. However, for shunt motor, if you are going to make voltage control, you should keep IF constant. How we can keep IF constant? This is by changing the resistance value or rheostat field value in order to keep IF constant. Okay. Why we need to do that? In order to vary the speed smoothly without affecting the machine flux. For a constant load torque, so if we consider constant load torque like that, شباب, this is now torque load constant. For a constant load torque, such as that applied by elevator or hoist, the speed will change linearly with Vt. There will be a linear change in speed. In an actual application, when the speed is changed by changing the terminal voltage, the armature current is kept constant. Again, in actual application, when speed is changed by changing the terminal voltage, the armature current is kept constant. So we need to keep the armature current constant in order to achieve certain torque for the machine. In order to do that, you have to make closed loop control. And this is called constant current control. So you make constant current control whatever the applied voltage made to the machine. So this is important for voltage control. You have to keep the armature current constant all the time. Why? We need the armature current to be constant in order to keep torque constant. This is for constant torque control. The advantages of this technique, it provides a smooth variation of speed control from 0 to base speed, wide range of speed control, easily controlled by solid state drives. We can easily apply many techniques using solid state. Solid states means power electronics. So by power electronic converters, we can easily make this control. Whatever the available supply, AC or DC, we have many circuits to achieve or to provide the required DC voltage to the motor. Also, constant current and torque are easily achieved. طبعا يا شباب the relation between current and torque is linear relation depending on the value of flux. So if the flux is constant, the relation is linear all of time. So keeping torque and current constant is very important. In induction machine, the relation between torque and current is not linear, like in DC motor. However, we have some adaptive control techniques making that. What is the name of this control technique? It's called direct torque control. Direct torque control makes the decoupling between flux and torque in order to keep torque constant like in DC motors. So we have advantage of DC motor, which does not exist in induction motor, which is the linear relation between torque and the current. However, we can make closed loop control in AC motors in order to keep current and torque in linear relation by closed loop control like torque or direct torque control. Fine. So this is the advantages of applying terminal voltage control for DC motors. Another well-known technique is the field current speed controls. In this method, speed is controlled by varying the value of IF. We have like field rheostat, okay? And we can change the value of RF in order to change the value of field current and flux. And in this way, if you increase the value of rheostat, this means the IF will be decreased and the speed will be increased. So as you can see here, this is the direction of decreasing IF, okay? And we have some limits for this control. We have RF control equals 0 here at that point, and this is the highest value of RF control, okay? And this is the relation between omega m and IF at different control value of resistance. There is a relation in order to check the value of required resistance of field control in order to control this current. However, this is in conventional drive as well. In advanced drives, we used power electronics instead of changing the value of rheostat. Okay, how we can make that? Simply by using DC chopper across a resistance. So we use, instead of manual rheostat, we use another technique based on DC choppers. We will see, inshallah, later the circuits that are used in order to control the values of field, voltage, and adding a resistance. Okay. One of the best control techniques, for the DC motors is to keeping control in zones. We said that we prefer voltage control, however, we cannot control the voltage overrated. And also, for field control, we do not prefer to reduce the field, to increase the field too much to avoid saturation. So we have like zones control from 0 speed to base speed or rated speed. We can keep our torque constant. This is by using V-terminal control or voltage control. And after that, we can make field control يا شباب or power control by keeping power constant, and in this case the torque will be decreased in over speed, or we can say that this is like field weakening يا شباب. This is like field weakening in induction motor, what we have discussed in induction motor, it's called field weakening. So this is the field weakening region here in DC motors. So for field weakening, if we reduce the field too much, this will, or we can operate the machine in constant power mode. So we have two modes of operation now. Constant torque, this is by keeping current constant during voltage control, and constant power. This is by keeping power constant while changing the value of field, increasing the value, reducing the value of field in order to make overspeed for the machine. However, the torque has to be reduced in order to avoid overload, okay, to avoid overloading our machine. تمام يا شباب? So, speed control beyond the base speed is obtained by decreasing the field current. This is at that region, okay, and called field weakening. And previous region here, we call it as constant power. Speed control from 0 to base speed is usually obtained by the armature voltage control, which is VT, and we keep torque or current constant. At the base speed, the armature terminal voltage is at its rated value. This point here, V terminal is rated. If the armature current is not to exceed its rated value, which is the heating limit of the machine, speed control beyond the base speed is restricted to constant power. Okay, شباب? So to avoid overloading our machine, we said that we can apply constant power. So this is, شباب, the most preferred method of controlling a DC motor. We can combine between voltage and field control and consider the operation at constant torque and constant power. Okay. Let's start solving some problems. I think a problem may take more than the remainder time. So we can start شباب solving problem إن شاء الله from the next class, and we can stop at that point here. Is there any question شباب? Any question regarding the today class?
Clear for now, Doctor.
Right. Okay, good يا شباب. Right. إن شاء الله just a reminder, I sent you some MCQs regarding induction motor. Please have a look, and if you have any question, don't hesitate to send me. The midterm exam will be next week, inshallah, so prepare yourself. The topics which will be covered in the midterm exam are all of topics related to induction and synchronous machine. Okay, so study well, inshallah, and everything will not be coming out of our class.
Yeah, Doctor, you're gonna send like on Sunday the link of the exam and other stuff?
For the exam, there will not be a link for exam in class, because all of class is already included in the Teams link in the same group. So no need for exam link. So we will use the same link for our class. Okay?
Okay, Doctor.
Lab was different because we collected, in the backup exam of lab, we collected 2 sections and 2 groups of teams. So I had to make another link. However, for the course exam, we don't need to make that, inshallah. Any questions, Shabab?